Usually when we talk about like a medical diagnosis, there's this inherent expectation of precision.
Right, yeah, like structural engineering or something.
Exactly. I mean, you break your arm, the X-ray shows that stark, jagged white line across the
It's
bones.
a completely binary state. Broken or not broken, it's clean, visible, and, well, easily categorized.
Yeah. But then you step into the world of software architecture, specifically data management, and suddenly that X-ray machine is just, it's completely broken.
Oh, absolutely.
We're looking at a structural landscape that is murky. It's layered in all these abstractions. And honestly, a lot of times it's just held together by duct tape.
More often than we'd like to admit, yeah.
Right. But what if a single package could bring that X-ray level of precision back to what is, frankly, a notoriously chaotic space?
That's the million-dollar question.
It really is. So today, we are unpacking a remarkably dense document. It's a README excerpt for a tool called @effectively/dash.
Yeah, and it's a fascinating read.
It is. And if you are currently evaluating back-end architectures, or, you're just intensely curious about the absolute bleeding edge of where our data is moving,
Well, it's just moving fast.
super fast. Well, this deep dive is going to challenge a lot of assumptions about how modern software is actually built.
Right off the bat, the document introduces Dash as a local-first storage and sync engine. It tells us right away that it's built around Squile. It features CRDT-friendly synchronization, and it supports this massive array of transport protocols.
I want to pause right there, actually, because the term local first gets thrown around so much in developer circles right now.
It's definitely the buzzword of the year.
Yeah, exactly. And it
Yeah.
usually implies that the app assumes the local device, like your phone or your laptop, is the primary source of truth.
Right, rather than constantly asking a cloud server for permission to, read or write data.
Exactly. But the authors of this package make what they call a, quote, fair brag.
I love that phrasing.
Me too. They state that this package doesn't just do one thing. It combines local execution, collaborative sync, presence helpers, reactive utilities, peer connectivity.
And an MCP server surface,
Yeah.
all into a single engine.
Right. So to understand why they consider that a fair brag, we really have to look at the architectural pain points of the past, decade?
At least a decade. For years, the industry standard has been to just separate these concerns entirely.
Like having different contractors for plumbing and electrical.
That's a great analogy. You have your local database layer over here, and you have your network synchronization layer over there.
And forcing those two to actually talk to each other has historically been just a massive headache.
Oh, a total nightmare.
Let's explore the mechanics of that headache, actually. Why is it so inherently difficult to connect a local database to a network sync layer?
Well, because fundamentally, they conceptualize data differently. Like, fundamentally.
How so?
So a traditional relational database, right, like SQLite,
Yeah.
it wants to neatly organize data into static tables and rows.
Right, it wants order.
Exactly. It expects to be the absolute, unquestioned boss of that state.
Okay, so what about the sync engine?
A collaborative sync engine, however, wants to break data down into a dynamic stream of events or operations. Operations that can be shared and merged with other users concurrently.
So it's constantly in motion.
Right. So when you try to bolt a stream-based sync engine onto a static, state-based database, you introduce this really clunky translation layer.
Like trying to translate a live sports broadcast into a static textbook in real time.
Exactly. You have to write all this extensive custom code just to keep the local disk state and the volatile network state in harmony.
And that's where things break.
Always. It almost inevitably leads to race conditions or these awful split-brain scenarios where, the network thinks one thing and the disk thinks another.
So by stating that local storage and collaborative sync live in the same package, Gash is basically claiming they have preemptively solved that translation problem.
Precisely. They're offering a fully unified architecture. Yeah. And if we look closely at the terminology in the what you get section of the README, it lists Dash as the main engine entry point.
Right.
And immediately below it, it lists create a Dash as a factory helper.
Okay, the factory helper concept really stands out there to me. It implies this isn't just some monolithic dependency you drop into your code base that completely takes over the runtime.
Right. In software design, a factory pattern is used to instantiate objects dynamically.
Meaning you build it when you need it.
Exactly. By providing create a dash as a factory, the architects are signaling that this complex engine is actually highly modular.
So it's not a singleton.
No, not at all. You can spin up a specific instance of the dash engine cleanly, pass in your specific configurations, and then just tear it down if needed.
Which is huge for testing, by the way.
Oh, it's a lifesaver for testing. It completely encapsulates all the heavy lifting of wiring the database to the network layer, hiding it behind this really clean instantiation method.
There's a distinct confidence, actually, in the way this document is written.
Very much so.
Yeah, like under the section titled, Why This README is Grounded, the authors explicitly state, Dash does not need a slogan to justify itself.
It's a really refreshing departure from typical developer tooling marketing.
Which is usually just completely saturated with hype and these abstract promises.
Right. AI this, blockchain that.
Exactly. But they are grounding their value proposition purely in utility and actually shipped code.
Which brings us to the actual utilities they're shipping. The document outlines a truly massive surface area for network connectivity.
Oh yeah, let's list them. It lists YJS, WebSocket, WebTransport, WebRTC, and optional auto-merge paths.
It's a lot.
It is a lot, and my immediate reaction to that list was, honestly, skepticism.
Really? Why?
Well, if you are building a tool designed to be hyper-efficient, why not just enforce a single, highly optimized transport method? Maintaining that many protocols seems like architectural bloat.
Well, it looks like bloat until you consider the wildly different network topologies that a local first application might find itself in.
Okay, fair. Let's unpack that.
Let's contrast WebSockets and WebRTC, for example.
Yeah.
So WebSockets provide a persistent bidirectional connection between a client and a central server.
Like a dedicated phone line to the cloud.
Right. If you're building an application that still relies on a central authority to, say, validate transactions or act as a main relay, WebSockets are totally essential.
But WebRTC fundamentally changes that topology.
Completely, because WebRTC is strictly peer-to-peer.
Right.
It allows two clients, say, two web browsers on two different laptops, to connect and stream data directly to each other. It bypasses the central server entirely.
Now, you do usually need a small signaling server at first.
Yes, just to exchange IP addresses initially.
Yeah.
But once they're connected, the payload travels directly between the devices.
Which is way more efficient.
Oh, drastically.
Yeah.
Think about it. If you and I are sitting in the same local network, working on a massive data set, sending all those bytes out to a cloud server in Virginia, just to route them back to the same room?
It's insane.
It is. It's incredibly inefficient. WebRTC solves that.
Okay, so by including both, Dash is remaining agnostic to the developer's network strategy.
Exactly.
But what about the data merging strategies? Because the document lists both YJS and auto-merge.
Right, the CRDTs.
Yeah, and for you, the listener, who might be familiar with CRDT's conflict-free replicated data types at a high level, you probably know it's the underlying tech that allows two people to edit a document offline and then merge it later without conflicts.
The Google Docs magic, essentially.
Exactly. But how do YJS and auto-merge differ mechanically? Why justify including both of them?
This is where we get away from treating CRDTs as just this, mathematical magic and look at the underlying structures.
Okay, pop the hood for us.
So CRDTs ensure consistency by mathematically guaranteeing that if two peers see the same set of operations, they will always arrive at the exact same state.
Regardless of the order those operations arrive.
Right. And they often use mechanisms like vector clocks.
Which is like a multi-dimensional timestamp, right?
Exactly. It tracks causal relationships between events to determine exactly what happened and when.
So if I type the word hello while offline, and you delete a paragraph while you're offline, the vector clocks help the system reconcile those actions when we eventually reconnect.
Yes, exactly. But here's the key difference. YJS and AutoMerge are optimized for very different data shapes.
Different shapes. How so?
YJS is heavily optimized for flat sequences, like rich text editing.
Okay.
Under the hood, it uses a doubly linked list structure where every single character or block has a unique identifier, which makes it incredibly fast for collaborative typing.
And auto-merge.
AutoMerge, on the other hand, was historically designed around complex, deeply nested JSON document structures.
So not just flat text.
No. It essentially turns a whole JSON object into a tree of operations.
Ah, okay. That perfectly explains the inclusion of both.
Right.
If your app is a collaborative text editor, you'd lean heavily toward the YJS path. But if you're syncing deeply nested configuration files or, like, complex game states, auto-merge might be the better fit.
Exactly. Dash is essentially giving you the option to hot swap your conflict resolution algorithm based on your specific domain.
That's incredibly powerful. And that modularity extends to how the synchronization itself is actually managed, doesn't it?
Yes, the text mentions peer sync and synchronizer factory. There's that word, factory again.
Meaning you aren't locked into a single background sync loop.
Right. A synchronizer factory implies that a developer can dynamically generate and configure synchronization processes based on real-time network conditions.
Well, that's smart, so it adapts.
Totally. If a user drops from a high-speed Wi-Fi connection to a spotty, 3G cellular network, the app could potentially tear down a high-bandwidth WebSocket synchronizer.
And spin up a highly throttled, batch-oriented WebRTC synchronizer on the fly.
Exactly, without restarting the app.
That level of dynamic control is so rare in out-of-the-box tools. And speaking of network states, the text specifically points out that presence helpers like get presence and update presence are included, quote, instead of left to the application.
Which is a massive architectural decision.
It is. Because presence, just knowing who is online and what they are currently interacting with, is notoriously difficult to build from scratch, especially in a decentralized environment.
It seems trivial on the surface, right?
Yeah. It's just a little green dot next to a user's avatar, or the Jane is typing indicator.
But underneath that little green dot is a distributed systems nightmare.
I can imagine.
In a traditional client-server model, presence is easy. The server knows who is physically connected to its sockets.
But in a local-first, potentially peer-to-peer network.
There is no central authority to ask, hey, is Jane online?
So how does the network figure it out?
Usually through gossip protocols and heartbeat mechanisms.
Gossip protocols, I love that term.
It's very descriptive. Clients constantly broadcast these tiny, I am alive messages to their peers.
And what if they don't? What about silent failures?
That's the hard part. What if Jane's device just loses power instantly? Her battery dies. It didn't send a graceful disconnect message.
The network is just waiting.
Right. The other peers have to run algorithms to realize, wait, we haven't heard Jane's heartbeat in 5 seconds. We must mark her as offline.
That sounds like a lot of overhead.
It is. Furthermore, present state is inherently ephemeral. You do not want to save a Jane is typing event to your permanent Squall database and sync it to your hard disk.
Because it's completely useless historical data. Nobody cares that Jane was typing a week ago.
Exactly. So by integrating getPresence directly into the engine, Dash provides a dedicated, highly optimized ephemeral data channel. It runs right alongside the permanent storage sync.
Okay, I see. So developers don't have to pollute their main database schema with ephemeral state.
Right. Nor do they have to write complex gossip protocols from scratch.
That really drives home the fully furnished nature of this engine. It's ready to live in.
Absolutely.
But let's look at the actual data traveling over these connections. We have our WebRTC highways, we have our YJS conflict resolution, but how is the data actually packaged?
This is where it gets really technical.
The document makes a very strong architectural stance in the Why People May Like It section. It says, flow frame payloads stay binary all the way down.
Binary all the way down. That is a phrase that carries a ton of weight in system design.
To appreciate it, we really need to understand the alternative, right? Which the document later refers to, almost mockingly, as legacy JSON.
I noticed that too. Referring to JSON as legacy is an incredibly aggressive flex.
It really is. I mean, JSON, or JavaScript Object Notation, is the undisputed lingua franca of the modern web. Literally every API, every web app relies on it.
It is ubiquitous because it is human readable. It's totally text-based. You can open a network payload in your browser's DevTools and read exactly what data is being sent.
But that human readability comes at a cost.
A massive cost to machine efficiency.
Let's make that abstract cost concrete for the listener. How exactly does parsing JSON slow down a system compared to binary?
Okay, so when a computer receives a JSON payload, it basically receives a long string of characters. To understand that data, the CPU has to read it sequentially.
Like a book.
Exactly. It has to scan character by character to find the opening bracket, then find the quotation marks to identify a key, then find the colon, then determine if the value after it is a string, a number, or a Boolean.
It's like reading a dense paragraph word by word just to extract a single noun.
Right. It requires a massive amount of string manipulation and memory allocation just to figure out what the data even is.
So much wasted energy.
Precisely. Now compare that to a highly structured binary payload. A binary codec doesn't use brackets or quotation marks or colons.
It just uses raw bytes.
Yes, it uses strict, predefined schemas. The computer knows without thinking that the first 4 bytes represent an integer, the next 8 bytes represent a timestamp, and so on.
So if JSON parsing is like reading a paragraph,
Mm-hmm.
parsing binary is like receiving a standardized tax form where the data you need is always in the exact same 1-inch box.
That is an excellent analogy.
The computer doesn't have to read or interpret anything. It just measures blindly to the correct offset and extracts the data instantly.
Boom. Exactly. By forcing flow-frame payloads to stay binary all the way down, the Dash engine is eliminating this massive CPU overhead of string parsing at the network layer.
Which means it can handle way more volume.
Thousands of discrete events per second, without bottlenecking the device's processor.
And the document lists several specific binary codecs that they utilize right out of the box.
Let's hear them.
There's the topology codec with GG binary defaults. There's the alphabet codec for packed alphabets, the bitwise codec for bitwise binary records, and finally the domain codec, which they specifically relegate to legacy JSON.
Each of these codecs tells us something really interesting about the extreme optimization happening under the hood here.
Let's start with the alphabet codec, packed alphabets.
That suggests they have implemented sophisticated compression algorithms for text strings. Instead of sending raw ASCII or UTF-8 characters over the wire, they likely map frequent strings or characters to highly compressed binary representations.
Kind of like a dictionary encoder.
Exactly like that.
And what about the bitwise codec?
Okay, so bitwise operations occur at the absolute lowest level of computing, directly manipulating ones and zeros.
Right.
If you have a data structure that contains, say, 32 Boolean true-false flags.
Like 32 checkboxes.
Yes. Sending that as JSON takes up a significant amount of text. You have to write true or false 32 times, plus the keys.
It's a lot of bytes for very little actual info.
Right. But using a bitwise codec, you can pack all 32 of those true-false states into a single 32-bit integer.
Oh, wow.
Just one number representing 32 different switches. It is the absolute maximum density of information possible.
And this focus on extreme data density is reflected in how they describe the storage itself. They list FlowFrame Engine and FrameDash as a, quote, frame-native storage and compatibility bridge.
Frame-native.
Yeah. What does the word frame imply here as opposed to like a traditional database row?
That's a crucial distinction. A relational database row represents a state, a fixed point.
Okay.
A frame conceptually aligns much closer to a discrete slice of time, like a frame in a video file or a packet in a continuous data stream.
So it's temporal.
Exactly. A frame-native architecture implies the engine isn't just storing static records. It is designed to ingest, sequence, and replay rapid, continuous streams of high-density events.
Which perfectly sets up the most astonishing part of this entire document.
The wildcards.
The wildcards. We understand the binary density. We understand the frame-based streaming architecture. But what kind of data streams actually require this level of optimization? Because the document lists tools that seem, honestly, entirely out of place for a general-purpose database.
It reveals use cases that completely push the boundaries of typical web or mobile apps.
I'll say, the text explicitly lists eye-tracking frame helpers and DNA helpers.
Wild.
When I read that, it totally broke my mental model of what this tool is for. Why on earth does a local-first storage and sync engine have built-in support for human eyes and biological genomes?
It suggests the authors recognize that the next generation of local-first applications won't just be collaborative to-do lists or chat apps. They will be processing massive, hardware-generated or biologically derived datasets locally, right at the edge.
Let's analyze the eye-tracking helpers first. The text mentions deterministic session stream aids, QDoc-backed session snapshots, and event frame encoding-decoding for Gnosis eye-tracking failures.
There's a lot to unpack there.
Let's start with determinism. Why is a deterministic session stream so vital for eye tracking?
Well, if you are building an application for spatial computing like an augmented reality headset, the hardware is generating eye tracking data at hundreds of frames per second.
Just constantly tracking your pupil.
Yes. And that data dictates exactly how the UI renders or how an avatar interacts. Determinism means that the sequence of events is mathematically guaranteed.
Meaning there's no ambiguity.
Right. If you process frames 1 through 10,000, you will always arrive at the exact same state every single time you run it.
So if the stream IDs aren't deterministic,
then network latency could cause frames to process out of order, which results in visual jitter or completely corrupted analysis.
and what about the QDoc-backed session snapshots? I mean, if an AR headset is generating hundreds of frames a second, that stream becomes massive very quickly.
Exactly, millions of frames in an hour. If a user takes off the headset and then puts it back on an hour later, the system cannot afford to replay millions of individual eye tracking frames from the very beginning of the session just to figure out the current state.
That would take forever.
It would. So a snapshot mechanism allows the engine to periodically take a compressed, highly queryable picture of the entire stream state at a specific moment.
Oh, so it acts like a save state in a video game.
Exactly like a save state. It acts as an anchor point. So the system only has to replay the handful of frames that occurred after the latest snapshot.
That makes perfect sense. Now, the most specific and intriguing feature there is the vent frame encoding-decoding for Gnosis eye tracking failures.
Gnosis implies very specific high-fidelity hardware.
And hardware is fundamentally imperfect, right?
Yeah, always. An eye tracker might lose sight of the pupil for just a fraction of a millisecond, maybe due to a blink or an odd reflection off a pair of glasses.
So the data just drops.
Right. And in a rigid traditional database system, a missing or corrupted frame might trigger a systemic error. It could cause the entire data pipeline to fail.
Or at the very least, it forces the developer to write incredibly complex error-catching logic at the application layer just to keep the app from crashing.
Exactly. But by introducing Event Frame natively, Dash provides a formalized mechanism to represent hardware failure within the binary stream itself.
How does that work?
It essentially says, hey, we expected a valid frame here, the hardware failed, so we are inserting a highly compressed event frame to represent that exact moment of failure.
Oh, so it preserves the chronological integrity of the stream.
Yes. The engine can decode that event frame on the other end and handle the drop gracefully without breaking the deterministic sequence. It literally treats hardware failure as a first-class citizen of the data stream.
That is profound resilience built right in.
It's beautiful engineering.
Now let's pivot to the biology, because honestly, that's an even bigger conceptual leap for me. The document mentions DNA helpers. Specifically, create pactin record, extract antiseeds, and extract DNA minimizers.
It is a massive conceptual leap. Human DNA is essentially the ultimate big data problem.
We're talking about billions of base pairs.
Right. A, C, T, G. Billions of them, representing massive strings of information.
So if I'm a researcher trying to compare genomic sequences, doing that in a cloud environment makes sense to me. You upload the data, you run it against a massive compute cluster in AWS, and you get the results.
Wow.
Why would you ever need local first helpers for DNA inside a tool like Dash?
For three main reasons: latency, privacy, and offline capabilities.
Okay, let's break those down.
Imagine bioinformatics software deployed in remote field research stations, places with absolutely zero internet access.
Right, out in the jungle somewhere.
Or think about clinical applications in a hospital that must process highly sensitive genomic data entirely on device to comply with strict medical privacy laws.
Oh, like HIPAA on steroids.
Exactly. Uploading that raw genomic data to a cloud server might be illegally or physically impossible.
But how does a local device like a standard iPad or a laptop handle a string of billions of characters without just completely freezing up?
That is exactly what the extract DNA minimizers and extract DNA seeds algorithms solve.
What are minimizers?
So in computational biology, comparing two massive DNA sequences, character by character, is computationally ruinous. It would take forever.
So what do they do?
Instead, algorithms break the sequences down into smaller substrings. They're called comers.
So it's essentially a hashing problem.
Basically, yes. A minimizer is a mathematical technique to find a highly representative, small, unique sequence, a seed, within that massive string.
Okay, so you're finding the most unique fingerprints within the DNA.
Right. By extracting minimizers, you create a highly efficient, compressed index of the genome. You can rapidly compare the minimizers of two different sequences locally to see if they overlap or share mutations.
Completely avoiding the need to process the whole sequence.
Exactly.
So by providing Create Pactin Record and the minimizer extraction tools natively, Dash is allowing developers to treat massive biological data sets with the same ease as they would a simple JSON object,
while maintaining the extreme efficiency of local binary execution.
It really proves the thesis that this engine is built for the absolute edge of complex data applications.
It definitely does. But, having this incredible back-end power is really only half the equation.
Right, because the data eventually has to be surfaced to a user interface.
The user has to see it.
Which brings us to the reactive utilities and resilience middleware built right into the package. The text highlights reactive helpers exported directly to the developer: signal, effect, computed, and live query.
Very familiar terms.
Yeah, for anyone familiar with modern front-end frameworks like React or Solid, These terms are the bedrock of reactivity.
They are. Reactivity is just the architectural pattern that ensures the user interface is a direct, automated reflection of the underlying state.
If the state changes, the UI updates automatically. No manual refresh required. But implementing reactivity at the database level is traditionally very different from implementing it in a front-end framework. How does a tool like LiveQuery function mechanically in this context?
Well, let's look at a legacy system.
Yeah.
In the past, if you wanted to know if the database had new data, the application had to continuously poll the database.
Meaning it literally asks, do you have new data? How about now? How about now?
Exactly. And polling is incredibly inefficient. It hogs CPU and absolutely drains battery life on mobile devices.
But a live query is different.
Very. A live query maintains a persistent, event-driven subscription directly to the database layer.
So the database pushes the update to the UI rather than the UI constantly asking for it.
Right. It reverses the flow. When a new flow frame arrives via WebRTC from a peer device, it updates the local SQLite disk.
Okay.
And instantly, the Dash engine evaluates its internal reactive graph. The live query recognizes the underlying data has mutated, it updates the derived computed states, it triggers any necessary side effects, and instantly pushes the new signal to the front-end framework.
Without the developer writing any glue code.
None. The developer doesn't have to wire that up. The data pipeline is fully reactive from the moment it hits the network socket all the way to the pixels rendering on the screen.
It's just an unbroken chain of reactivity.
It's beautiful.
It is. But let's look at the reality of networks, because networks are hostile and highly prone to failure.
Terrible.
Yeah. And the document details built-in error middleware. It lists retry, rate limiting, and error handling helpers.
I like to think of this as the armor around the engine.
That's a good way to put it.
Because if you are syncing millions of deterministic eye-tracking frames, network jitter is just inevitable. Packets will drop. The built-in retry mechanisms likely implement complex back-off algorithms.
Like exponential back-off with jitter.
Exactly. To ensure that a briefly dropped connection doesn't instantly result in a flood of simultaneous retry requests that just completely crash the local network.
Right, you don't want to DDoS yourself. And the rate limiting is equally important, especially in a peer-to-peer WebRTC scenario.
Right. Oh, absolutely critical.
Like if I connect to a peer device that has suddenly gone rogue, and it's trying to blast me with gigabytes of corrupted DNA records.
What happens?
The local engine needs a mechanism to throttle or just drop that connection before it completely overwhelms my local device's memory.
Right. The fact that Dash provides this middleware out of the box as part of the core engine proves it is actually designed for hostile, real-world deployments, not just clean lab environments.
Now, there is one more component in the What You Get list that really caught my eye, especially regarding the future of application architecture. It simply lists MCP server. MCP server surface.
Ah, yes, MCP.
Which stands for Model Context Protocol. This is a relatively new standard, but it is gaining massive traction in the AI space right now.
It is blowing up.
So what does it actually do here?
So large language models and local AI agents need context to be useful.
Right. They need to know what you're working on.
Exactly. If you have a local AI assistant running on your machine and you want it to, say, summarize your local project files, it needs a standardized way to read that data.
It needs an API.
Yes. The Model Context Protocol provides exactly that, a secure, highly structured interface for applications to expose their local data to an AI model.
Okay, so by embedding an MCP server surface directly into the Dash engine, the authors are setting up the database to natively communicate with local AI models.
Out of the box.
That is wild. An AI agent could securely query the local SQLite database. It could interpret the binary flow frames or maybe even analyze those extracted DNA minimizers we talked about.
All entirely on device.
Without exfiltrating any of that sensitive data to a cloud provider's API.
Exactly. No sending your genome to OpenAI. It stays on your laptop. It essentially transforms the local database from a passive storage bucket into an active participant in an AI-driven workflow.
It is incredibly forward-thinking.
It really is.
Okay, so we've covered the underlying architecture, we've talked about the wild data types, and the reactive front end. I want to bring this all together by looking at how the engine handles arguably the most difficult part of local-first development.
The reunion.
The reunion after separation, yes.
Synchronization when both peers are online and talking is, frankly, a solved problem.
It's easy.
It is. The true test of a local-first engine is how it handles the catch-up mechanics after a device has been completely offline for hours or even days.
And the document highlights a very specific mechanic for this. It states, flow frame sync provider. Catch-up sync-sense replay batching is enabled by default for relay-heavy streams.
That is a dense sentence.
It is. Let's break that down for the listener.
Yeah.
So when my device reconnects to the network, it initiates a sync-sense query.
Right.
Basically, it's asking the network for every single event that occurred since my last known vector clock state.
Correct. Now imagine you are syncing a relay-heavy stream, which, based on our earlier discussion, could be a continuous stream of biometric data or high-frequency hardware telemetry.
Like the eye tracking data.
Yes. During your time offline, tens of thousands of frames may have been generated by your peers.
So I reconnect, and suddenly there's a flood of data. If the network sends those 10,000 frames to my device, and the Dash engine processes them individually,
Pushing 10,000 sequential updates through the reactive live query pipeline straight to the UI,
your application will completely lock up.
it will freeze solid. The UI thread in JavaScript, as you know, is single-threaded.
Right.
If it is forced to re-render 10,000 times in a matter of a few seconds, the app just becomes totally unresponsive.
You'll just get the beach ball of death.
Exactly. This is exactly why replay batching is enabled by default.
How does the batching work?
The engine basically intercepts that massive influx of historical frames. It processes them in the background, updates the underlying script state in a single massive transaction, and then, and this is the key, it emits exactly one update to the UI.
So it sacrifices seeing the history play out visually in order to achieve instant responsiveness.
Yes, it just jumps to the final state.
But that actually brings up a really interesting conflict in the documentation.
They override.
Yes. The document explicitly points out how to disable this optimization.
Right.
It says setBashing.enabled, false to force raw, per frame replay.
Right.
If batching prevents the application from freezing, why on earth would a developer intentionally turn it off?
Because in certain highly specific analytical domains, the sequence of historical events is actually way more valuable than just quickly arriving in the final state.
Give me an example.
Think back to the eye tracking data. If you were building a diagnostic playback tool for neurologists,
Okay.
and you batch 10 seconds of rapid eye movements into a single UI update.
The doctor only sees where the eye ended up.
Exactly. They completely miss the crucial microtremors, the saccades, all the nuances that occurred during those 10 seconds.
The journey is the data, not the destination.
Exactly. By forcing raw per frame replay, the engine feeds the historical frames into the reactive pipeline one by one. It preserves the exact chronological sequence and the timing.
So it allows the UI to physically replay the offline events exactly as if they were happening live.
Yes, it puts an immense strain on the UI thread, obviously, but for highly sensitive temporal analysis, it is an absolute requirement.
That's fascinating. So Dash provides the optimization by default for performance, but it leaves that deterministic override available for deep analysis.
It gives you the choice.
This has been just a relentless deconstruction of an incredibly dense architectural philosophy.
We really dug into.
We did. We started with the promise of a fair brag, a tool that bundles storage, sync, peer connectivity, and reactivity all into one package.
And we found an engine that fundamentally rethinks how data moves at the edge.
It completely discards text-based serialization in favor of these hyperdense binary codecs.
It treats continuous frames as a native storage mechanism.
And it provides dedicated pipelines for everything from ephemeral user presence to proprietary hardware failures, all the way to genomic sequencing.
It's incredibly ambitious.
It really is. So if you're listening to this and you are an architect, a developer, just someone observing where computing is heading, what is the ultimate takeaway here?
The baseline expectations for local-first software are shifting dramatically.
Right. The era of writing extensive, brittle translation code just to force a local database to talk to a network socket, that era is ending.
We are moving toward unified, hyper-specialized engines capable of handling staggering data density right on the device in your pocket.
And it leaves us with a really compelling final thought, actually.
What's that?
Well, we spent a significant amount of time exploring the native inclusions of eye-tracking determinism and DNA minimizer algorithm.
Right.
If a generalized open-source sync engine now comes pre-packaged with the mathematical tools required to parse the human genome and process sub-millisecond biological hardware telemetry.
Then what does that indicate about the complexity of the mainstream applications we are about to see deployed?
Exactly. It suggests the boundary between massive biological computation and everyday application development is just disappearing.
It does. We are stepping into an era where processing millions of biometrically derived data points is no longer restricted to supercomputers and university research labs.
That data is becoming just another standard binary payload.
Synced peer-to-peer and processed seamlessly on our local devices.
It is a vastly different reality than the simple, clean X-ray we envisioned at the start of this deep dive.
The architecture is dense, yes, but the capabilities are truly unprecedented.
They are. Thank you for joining us on this deep dive into the underlying mechanics of modern data. Keep questioning the structural foundations of the tools you use, and we will catch you on the next one.